Hello everyone, welcome back to LeetCode Daily Live where I do the daily question raw and uncut. So we have a hard today, it's called find the count of good integers. So what are we given? So we have n and k, and oh, n and k are both very small. So I think we are looking at some exponential algorithm or like factorial, but let's see. So yeah, you're given we're given n and k. So X is called a K palindromic if it is a palindrome, right? So palindrome just means like if you reverse it, it's the same thing. X is divisible by K, right? So K would be like 1 to 9 and N would be 1 to 10. Um, hmm. So an integer is called good if its digits can be rearranged to form a K palindromic integer. So for example, for k is equal to 2. So yeah, so 2020 can be rearranged to like 2002. Wait, but 1010 cannot. Oh yeah, because like if k is 2, then like the only thing you can do is like you can do like 01, but then like 1001, but like obviously that wouldn't work. To return a count of good integers containing n digits. Ah, okay, I see why this is hard. Cause like you can have 10 digits, and like obviously you can't brute force all of them, so you need some like quick ways to calculate them. Ah, okay. Now that makes a hard question then. So note that any integer must not have leading zeros. So neither before nor after the rearrangement. Right, yeah, so that means like you can't rearrange 1010 to 101. Right, so, well, obviously you can't brute force this. So we have to think about, yeah, we have to think about how we want to go with this actually. So, yeah, also, like, would different k means different algorithm? Cause like, um, so let's say k is 2, right? Um, so if k is 2, that means like our number has to be like has to end with an even number. Like when it is like 3 or 9, like the sum of all your digits has to be divisible by 3 or 9. But when you have like something like 7, it's not too obvious what to do. Um, yeah. But I'm guessing like because of something like 7, we do need to like check by dividing k and see whether it works. Hmm. Yeah, but like obviously we can't check every number, which I think that like this is what makes this question hard, perhaps. Yeah. Hmm. Yeah. Let's see. Let's look at some examples to like, I guess, try to see what we can do here. So, when n is 3, k is 5. Right. So there are like 27. So it says like 551. Right. Because like you can arrange to form 515. Yeah. Like I think like for 1 to 9, there are good ways of doing those. But then when it gets to something like 7, like when k is 7, like it just makes things a lot harder to deal with. Hmm. Yeah, but let's see. Let's see what we can work with here. Yeah, actually, I think like for 7, there's like some rules for that as well. But it's like I don't think it will help too much. Hmm. Yeah. We do you have to like really think about this one? Yeah. Also, like one idea is so let's say n is even for now, I guess. Um, wait, actually, if we find all the palindromes for that digits, well, yeah, if we find all the palindromes, I have an idea. It's kind of cheating, but if we add a test case, so n is 10, k is 1, we can see the maximum number of palindromes we can get. Yeah, so let's cheat a tiny bit. See what the expected. Wait, only 27. Oh, okay. Okay, yeah, you can have a lot. What about like 9? So um yeah, so I think 10 and 1 will give the most. Oh, actually 9 and 10 are pretty similar in terms of size. Right, but what this tells us is that I think the actual palindromes, like the actual k palindromes that we can generate, are probably a number even smaller than this, right? So perhaps we can find all of them, maybe. Yeah, wait, let's actually like try to work out. Um, so if n is 9, how many palindromes can we have? So we can have, so in the middle, yeah, so in the middle we have how many choices? We have, it can be 0 to 9. The first digit has to be 1 to 9. But this has to be the same as this reversed, right? So we only have to like worry about the front basically. And like all of these can be like 0 to 9 as well. So that means we have like 9 times 10 to the power of 4. So actually we only have 90,000 palindromes that we can generate. And what about n equals 10? So again, we have something like this. This has to be 1 to 9. Oh, I should probably draw these as well. So this is like the mirror, the reflection axis, right? All these are 0 to 9s. So again, we actually only have 90,000 palindromes. So if we have a quick way to calculate for each palindrome, how many like rearrangements we can get? Wait a second. What is the question asking actually? So 2020 is a, yeah, okay. So if we look at the example, so 551 is a good integer because it can be arranged into 515. So what does that mean? It means that when we have 515, technically we can just generate like all the different combinations, I guess. So like because we know this works, right? And like obviously that falls into the constraint as well. Wait, but then there's another thing. So like if we work backwards, we have a bunch of like we have like at most 90,000 palindromes, right? But not all of them are divisible by like whatever k is. But we should assume that we need all of them because like if k equals 1, then we don't really have that constraint, right? So like I'm just counting the number, like count the number of operations we have to do. Yeah. But like if 515 works, that means, well, how many like how many 3-digit letters can we actually generate here? Like from these 3 digits. Well, we can do 551. We can do like 155. But actually, this is a pretty well-known like permutation problem, I think. Um, so if you have 2 1s, so you have like 2 1s, and then you have, oh wait, you have 1 1, and then you have 2 5s. Um, that means you have like 3 factorial ways of like of like to rearrange like all these digits, right? But then half of them are going to be the same because, like, for example, if I put the first 5 here and put the second 5 here, that's the same as putting the second 5 here and the first 5 here, right? So like hence we have a duplicate of, like we have a duplicate for every number we generated. So like that's why we divide by 2. If you have like 3 5s, well, you have like 3, like for every like number you generated, you have like 3 5s, which, well, it'll basically generate this 6 times. Yeah, so it's a pretty like well-known permutation problem. But yeah, that's how you like calculate it quickly. So yeah, we kind of have the idea on how to do it now. But we still have to worry about one thing, which is when we have like, are we going to have any like overlap? So for example, yeah, what is a good example? Yeah, okay. So let's say we have like 1 2 3 2 1, and then we have 2 1 3 1 2. So both of these are palindromes, right? So if we are generating all the palindromes, and let's say both of them work. So let's say like k is equal to 1 in this case. Well, actually, our digits are the same here. So we don't actually like want to find the number of rearrangements we can do that actually like suits the case. Yeah, because like for example, like we can generate well, we can make like 1 1 2 2 3 from both of these, right? So that means like if we found another palindrome with the exact same digits, we should just ignore it. So we probably like need to use like a scene set or something like that. Like we have to use a set to like keep track. Maybe that'll work. But yeah, the last thing is, well, I said last thing before, but like we actually have like another like really big issue, which is what should we do for, oh, I'm hallucinating. So so the final palindrome has to be divisible by k. So actually, yes, we can just generate all the palindromes, and then we can check for each of them whether we have seen like the exact same like digits before, or have we or whether that palindrome like and that palindrome is divisible by whatever number we want, and then we want to generate like all the possible permutations. So yeah, actually, I think we can start coding now. Yeah, well, I kind of did cheat here a tiny bit, which is a bit unethical, but yeah, that kind of helped me understand that we actually do have enough time to generate all the palindromes. So I guess we want to do it as a string. So what we can do is, oh wait, just one last thing. So when we are generating for, let's say, something like 10101, well, actually, we cannot choose any number that starts with a 0, right? So for example, we can't. So this is not a valid number because it doesn't actually contain n digits because this is a leading 0. So we need a way to calculate, like, if we have zeros, like how many rearrangements we generate that has 0 like at the front, I think. Wait, actually, yeah, if we think of this as like a math, yeah, actually this question is extremely mathy. But if we think about it, our first number can't be any it can't be any zeros, right? So in this case we have like 3 ones and then we have like 2 zeros. So that means like for the first number we actually only have 3 possibilities. And then for the next one, yeah, what should we do for the next one? Well, yeah, actually, like for the rest, it would just be like 4, 3, 2, 1, because like we can put them however we want. But then the question is, are we still like just dividing, like for the duplicate thing, like is our original like division things, like that, does it still work? So yeah, we have to find that out as well. So yeah, actually, I think it still stands. Yeah, because again, like you can put the first one, the second one, or the third one at the beginning, and then the rest. Well, let's say we have like a 1 here and a 1 here. Well, again, like we can technically rearrange these in 6 different ways. Like let's say like each of them are labeled or something. We can rearrange these in 6 ways, right? And we'll still get the same number. So yes, actually, like the rule here still stands, but it just means like if we have any zeros, we just don't want to count them. But yeah, I think we can start coding. Yeah, we should start coding. So I'm going to abstract the count numbers thing first. So this is going to count like if we have a palindrome. So we have a palindrome. What should it be? Maybe a string. Yeah, I think like it doesn't really matter like what numbers they are this time around, cause like we're more interested in the actual digits this time. So yeah. So we want to return like an int, which is like the count of like the rearrangements, like or all the good integers that uses like our current palindrome's number. So we just pass that, and then yeah, and then we want to generate all the palindromes in a quick way. So that means, actually, what does that mean? Yeah, I think like if we have so we can just generate like 1/2 of it. So that means we kind of have to like separate them. Yeah, I'm just thinking of a nice way of doing this instead of like writing really disgusting code. Yeah, like obviously we have the n is odd case and the n is even case. So we have to worry about that as well. But I think like we can still generate like 1/2 of it first. So so what can we do? We can do something like for I in range. I think 10 to the power of n divided by 2. So for example, if this is 10 Well, actually, we only want 5 digits, right? Wait, is that true? Yeah, we only want 5 digits. So, n divided by 2. So, let's say like n is 10. So, this is going to be 5 minus 1. It's going to be 4. So, that means we are going to generate. Wait, actually, no. We do want it to be up to 100,000. The reason is if we are generating 1/2 of, let's say, like n equals 10, right? Well, that means we want to generate from 10,000 all the way to that, right? So yeah, we do need to go from like 1 to 10,000, and well, we can just say like if the number of digits in 1 is like not like if the number of digits are not enough, then like we can just discard them. So that's only going to be like 10,000 more operations, which shouldn't be too bad. Yeah, I guess we don't really want to turn it into a string because it is a bit slow. I think it should still be quick enough. So I'll just do that. So first of all, we want to check. So we want to check enough digits. So if the length of string I is smaller than n divided by 2. Well, yeah, so I think like we will just keep going back to the like n equals 9 or n equals 10 case. So if n is equal to 9, that means we want to generate from like numbers from 1,000 to 9999, right? And like this will be 4, so that means this will be 10k, so that'll work. And we are checking if the number of digits, like if we have 4 digits right here, and if it is 10, like it will be 5 digits. So yeah, that will work. So if it is smaller, we just want to continue. We don't actually want to deal with this anymore. I guess we can do like string here, because we need that. We need that in the future anyways. Yeah, we can do that. Yeah, so we're not going to worry about the integer anymore. I guess we still have to worry about the division thing. So, yeah, so what else do we have to check? Well, I think like at this point, we want to generate, the actual palindrome now. So, generate the actual palindrome number. So we'll call it like P. Right, but then if it is odd, we actually have we actually have to do a different thing. Yeah, actually, is there a better way? Yeah, I don't. So the original thing I thought of is like, if we generate like the first half, like let's say if it is odd, right, and then like we can put like 0 to 9 here, and then we do that. But actually, I don't think that's a good way of doing it. What if we just generate all of these, and then like if it is odd, we just only copy like the first half of digits over to here. Like, isn't that a bit better? Yeah, so actually, we should have a function called like generate palindrome. And then, so instead of doing this here, we're going to do n plus 1. So that means like, if we have 9 digits, we are going to generate like from 10,000 to 100,000 as well. So we're going to include the middle number. And actually, would that cause any issue? Well, I don't think so, because we have 5 digits here. And what is our constraint? Well, the first letter the first digit has to be 1 to 9. The rest has to be like 0 to 9, right? So what does that mean? That really just means it has to be well it has to be, well, 10k like all the way up to 100k. So well, yeah, I think that will also work. But that means we probably have to change this as well. So yeah, we want this instead now. So we want to actually generate the palindrome. So palindrome, gen palindrome, and we want to put in our current string that we have, I think. So yeah, so we have a palindrome, which is a string, and then we want to also generate a string. So now we have two cases, right? So so if n is even, then it is a very easy case. So all we have to do is we want to return palindrome plus the reverse of that palindrome, right? So you just want to do like reversed palindrome, and we add them together, so that will make us the palindrome we want. But if it is odd, so odd here, we'll do even here. Well, actually, it shouldn't be too different, but it just means like we need to first well, actually no, we can still reverse the palindrome, but then when we reverse it, we want to get rid of the first character, because like the last character in palindrome would be the middle number for the odd case, right? If you flip it, it will be the first character. So we can just do this to get rid of the first character. Yeah, so we can do that. So we generate the palindrome, and then we have to check if divisible by k. So so we do have to turn it back into an int here for a bit. So divisible. So I guess this is a bit more clearer. But yeah, if it is not divisible, we just want to continue. So what is the next thing we have to do? We also have to check whether the number of digits are like we have to check whether we have seen those number of digits yet. So check whether we have seen the exact digits. Yeah, the exact digits, permutation, something like that. So how do we do that? Well, we have to find out well, the number of digits. So we can just do something like this. So 0 for in range 10, so that represents like the count for 0 to 9. And then we can just loop through our palindrome. So for digit in palindrome, we just want num digits. So we need a way to map our digits into the correct index. So I think to do this in Python, we need the ordinal of the character and then minus the ordinal of 0. Yeah, because like these are all like 0 to 9, we're representing that in like the character form, right? Wait, actually, there's a way nicer way. We can just turn this into an int. So if we do that, we just add 1. So we found that digit there, and then we just want to have a scene set up here. So if we should turn it into a tuple, because sets have to be like the elements in sets have to be like immutable. So if that's true in scene, well, we also want to continue. So at this point, we have found a unique palindrome. So we want to find the number of ways we can rearrange to form unique numbers, and we'll pass that to count nums. So count nums, we'll pass in the palindrome, and then we should have a total, and then at the end we can return total. Right, so we also need a total here then. Yeah, so now we only have this this function here left to write up. Yeah, but this is also like the hardest part to write, so bear with me. Yeah, so yeah, I guess the first thing we want to do we actually kind of want this to be in a function as well, I think. Yeah, actually let's put that in a function, because we need that in count nums as well. So well, actually, do we? Can we just pass that in as a parameter? Then we don't actually even need the palindrome. Like, we just need to know what digits we have, right? Yeah, so we don't have to worry about that at all. Okay, so yeah, we can just pass in number of digits here. Oh yeah, we should not forget about having to let me put this back in here first. Yeah, but if the tuple is not seen, we want to add that into scene. So we make sure we don't look at that later. So but we can look at like num digits now. So number of digits. So at this point we are guaranteed we have n digits, and we also don't have to worry about the k thing anymore. So we want to find out how many numbers we can generate. So I think we can just do something like return. Actually, let's not do return. So yeah, let's just do like count. So what do we have? So for the first digit, well, it can't be any 0 digits, right? So we will just do that. So like, because we have n digits, and any digits that are not 0 we can put at the front. So that's why we'll do that. And then for the rest, it will just be factorial. What is the? I think it's like math.factorial. That means we have to import math. So import math. So factorial, we want the factorial of n minus 1. Because, well, that's the number of ways you can rearrange the rest of the numbers. But then we also have to count the duplicates now. So yeah, I guess like what we can do is well, actually, if zeros are, yeah, okay. So what we want to do is like for I in range 10. So we basically look at all the digits. So if num digits, wait, actually, yeah, we don't even need this, because like 0 factorial is 1. So we just want to do count, and we want to divide it by the factorial of number of digits I. So that's basically like the duplicate thing we talked about here. So yeah, actually after this, I think we can just return counts. On paper, we have all the things needed. I'm not sure if we will get the right answer though. Okay, reversed object is not subscriptable. Okay, yeah, that's just we have to turn it into a list. A list? A string? Yeah, we have to turn it into a string. So string. I'm pretty sure I put the bracket in the wrong place. Yeah, to put it here. Yeah, so we turn it into a string and it should work. Invalid literal. Where is it? Here. We get palindrome. So it is here. Or do we have to turn it into a list and then a string? That's kind of annoying, not gonna lie. Yeah, so let's just turn it into a list and that string. Yeah, I thought string, well, like actually what string is doing is like this is a reversed object, right? So what string does is it literally turns it into like the reverse object string, which looks something like this. So now that should work. I'm not sure if, like, I'm a bit scared that it will be too slow up there. We're still printing like wrong things though. Right, so if we reverse the palindrome, we turn it into a list. Oh. Yeah. We shouldn't. If we use string, it'll just turn it into like it will turn it into like a visible kind of list. Oh, okay. And it works for these as well, so yeah, I'm pretty confident it works. Nice. Yeah, this question is I find this question very fun because like it touches a lot of math stuff, and yeah, I guess it's like very interesting as well. Like there are a lot of things you have to notice. So like for example, you have the number of palindromes you can actually generate, like with n equals 10. So if you have 10 digits, like how many you can generate, and also I guess like the heart of this question is this part, like where you have to use like the permutations and like the rearrangement formula, to actually like get the count very quickly. But yeah, I actually really like this question. And yeah, thanks for watching, and I'll see you tomorrow. Bye.